Okay, we're just going to look at these different ways of expressing acceleration. And we might just start off with talking about displacement at the beginning. And often we use x to denote displacement. Okay, it's very similar to distance, except it has direction as well. Now, if I was to differentiate displacement in terms of time, okay, this, by definition, gives us the velocity, which is similar to speed, but with direction as well. So if we look at this dx means infinitely small change in x divided by an infinitely small change in time. Okay, it gives us the velocity. Now think back to your speed formula. Speed is distance divided by time. Now, these two are very similar. Velocity is very similar to speed, and displacement is very similar to distance. So we can think of it as being that same sort of format. Okay, so that's dx dt. Now if I go one more step, if I differentiate it again in terms of time, this dx dt, okay, that would be equal to d squared x dt squared. And again, by definition, what we're looking at here is the change in velocity this time, because this is velocity, change in velocity in relation to time. Okay, so when I'm looking at that, it's our acceleration by definition. Okay, so there's one of our expressions for acceleration, which we've got here. Okay, now we often use v to denote velocity. Okay, so again, just like I did up here, if I differentiate velocity in terms of time, of course, we get acceleration, just like I spoke about before. Okay, so there's our second expression for acceleration. Now from here, if I use, we know this is acceleration, if I use the chain rule, say dv dx times by dx dt, okay, so we still cancel out, we still get dv dx, dv dt, sorry. So if we do that, I realize that this part here, dx dt, we worked it out before, dx dt is the velocity. Okay, so I could write this dv dt, which we know is the same as acceleration, okay, as being equal to dv dx times by velocity. Or, if I switch it around, dv dt is equal to velocity times by dv dx. And again, there is my third